channel Knowledge of, please subscribe to your channel and click the bell icon for the latest update. Today we're going to start with your physics class 11th class. This is your class 36 where we had done 35 classes in the last session. This is your unit 5, which is your laws of motion. So that we'll discuss here. In the last classes we had completed laws of inertia and even the Newton's first law of motion as well. Today we'll start discussing about Newton's second law of motion. So here we go for the same, and that we have follows. But before starting with the same, it's a huge request to all the viewers to please go ahead with like, share and subscribe so that many and maximum people can get the information at once, and even you can also enjoy the video as well. So let's start with Newton's second law of motion. Okay. So here the first law we'll discuss in the detail, and now we'll discuss the second law here, which is the first law that refers to the simple case, which that the net external force on a body is 0, and on the same way the second law of motion refers to the general situation when there is a net external force acting on the body. It relates the net external force to the acceleration of the body, and whereas in talking about here in the detail when in terms of momentum we'll discuss for the second law of motion. Momentum of a body is defined to be the product of its mass and velocity, and it is denoted by p, small p. So let's go for it. Momentum of a body is defined to be the product of its mass and velocity, and it's going to come. So momentum is clearly a vector quantity. In the same way, here that the following common experiences indicate that the importance of the quantity of considering an effect of force on motion. Suppose a lightweight vehicle, that's say a small car, and a heavyweight vehicle, say a loaded truck, are parked on a horizontal road. We all know that a much greater force is needed to push the truck than the car to bring them to the same speed in the same time. Similarly, a greater opposing force is needed to stop the heavy body than the light body in the same time if they are moving with the same speed. And if two stones, one light and the other heavy, are dropped from the top of a building in a car, or a person on a ground will find it easier to catch the light stone than the heavy stone. The mass of the body is thus an important parameter that determines the effect of force on its motion. Speed is another important parameter to consider. A bullet fired by a gun that can easily pierce human tissue before it stops, resulting in its casualty. The same bullet fired with moderate speed will not cause much damage. Thus, for a given mass of the greater speed, the greater is the opposing force needed to stop the body in a certain time. Taken together, the product of mass and the velocity, that is the momentum, is evidently a relevant variable of motion. The greater the change in the momentum is in a given time, the greater is the force that needs to be applied. Where a seasoned cricketer that catches a cricket ball coming in with a great speed far more easily than novice, and who can hurt his hand in the act. One reason is that the cricketer allow a longer time for his hand to stop the ball. As you may have noticed, he draws the hands backward, the act of catching the ball. Where the novice, on the other hand, keeps his hand fixed and tries to catch the ball. Almost instantly, he needs to provide a much greater force to stop the ball instantly, and that this hurts. And the conclusion is clear. Force not only depends on the change in momentum, but also on how fast the change is brought about, and the same change in momentum brought about in the shorter time needs a greater applied force. In short, greater the rate change of momentum and the greater the force is. On the same way, force not only depends on the change in the momentum, but also on how fast the change is brought about. And a seasoned cricketer draws his hand during a catch, allowing a greater time for the ball to stop, and hence requires a smaller force. So observation that confirms that the product of the mass and the velocity, that is the momentum, is basic to the effect of the forces on motion. And suppose a fixed force is applied for a certain interval of time on two bodies of different masses, initially at rest. That is, the lighter body picks up the greater speed than the heavier body. However, at the end of the time interval, observation shows that each body acquires the same momentum. Thus, the same forces for the same time cause the same changes in the momentum for a different bodies here. And this is a crucial clues to the second law of motion. And for the same, in the detail, in our preceding observation, the vector character of momentum that have not been evident. In an example so far, momentum and change and momentum both have the same direction, but this is not always the case. Suppose the stone is rotated with uniform speed in a horizontal plane by means of a string. The magnitude of momentum is fixed, but its direction changes, and a force is needed to cause this change in momentum vector. Although this force is provided by our hand through the string, experience suggests that our hand needs to exert a greater force. If the stone is rotated at greater speed or in a circle of smaller radius, or both, this corresponds to the greater acceleration and equivalently a greater rate of change in momentum. And basically, that is the momentum vector, and that suggests the greater and the rate change in the momentum vector, that is greater in the force applied. On same way here, force is necessary for changing the directions of momentum. Even if its magnitude is constant, we can feel the while rotating a stone in a horizontal circle with uniform speed by means of a string. These qualitative observation leads to the second law of motion, that is expressed by the Newton as follows. second laws of motion, we'll write it down. That is the rate of change of momentum of a body is directly proportional to applied force and takes place in the direction in which the force acts. So the rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Thus, if under the action of forces F for a time here, that is interval delta t, the velocity of a body of mass m changes from v to v plus delta v, that is the initial momentum, where p is equals to mv, and changes to delta p. So let's get started here. Changes to delta p, m delta v, according to the second law. Force equals to delta p by delta t, or F equals to delta p. Where k is constant of proportionality. Taking the limit delta t tends to 0, the term delta p and delta t becomes the derivative of differential coefficient of p with respect to t, that is denoted by dp by dt, and thus dp equals to k dp by dt. For a body of a fixed mass, dp by dt equals to d by t md, mdv by dt equals to ma. That is the second law that also can be written as F equals to k ma, which shows that the force is proportional to the product of mass and acceleration. Thus, the unit of force that has not been defined so far. In fact, we use which is your F equals to k ma. That is, to define the unit of a force. We therefore have a liberty to choose any constant value for k. For simplicity, we choose k equals to I, and then k equals to 1, that is the second law, and for k equals to 1, equals to dp by dt, which is equals to n. And the SI unit for force is 1, that causes an acceleration of 1 meter second square to a mass of 1 kg, and this unit is also known as Newton. So 1 Newton equals to 1 kg meter second inverse square. Let us note that the stage some important points about the second law, which is we have some points we'll be determining that. The first point, in the second law, F equals to D0, that implies, in the same way, that implies A equals to 0, and the second law is obviously consistent with the first law. So we discussed here, and that we have to discuss many more related to it. For the same, we will be having to discuss about the detailed questions as well. So here we go. So the first point, the states that some points of the second law. The first point is, in the second law, F equals to 0 implies A equals to 0. The second law is obviously consistent with the first law. Now talk about the second law of motion of a vector law, that is. So here we're gonna end up with. Thank you. Hope you enjoyed this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Thank you.